Good morning. My name is Dr. Aber. I'm going to start with this. It is pronounced a bear. I know, messes with everybody. Most of you saw a Phantom R and called me Herbert. Believe it or not, in South Louisiana, it's the functional equivalent of Smith. It is as common as dirt. Across the Sabine or Pearl River, it becomes the most exotic thing anyone's ever seen. What messes with English speakers? The first and last letters are both silent. I don't know how many of you have ever seen the little thing on Facebook or somewhere online where they have a paragraph written. All the words are jumbled, but you can still read the whole thing without any problem. Everybody seen that? That's because as long as the first and last letters are right, your brain will sort the middle. First and last letters are silent, messes with everyone. That's how you pronounce my name. Where's my erasers? And how many of you have been logged into the online classroom on Canvas yet? How many of you saw the video of the first lecture that they canceled because of weather? And how many of you have actually done the homework assignment? Excellent. Y'all can turn your homework in. The rest of you can turn it in late. At some point, I will have to set a limit on how late can be before it just becomes pointless. But for now, consider yourself with an extra week to get last week's homework done. If you looked at the syllabus, you're probably a little bit worried because you know that next week we have a first exam that covers last week, which was canceled, and this week, which we're just about to cover. You'll also notice I put in a day this coming Thursday for us to all review both chapters before the exam on next Tuesday. So I think everybody should be okay, even though we did lose a day to bad weather. You'll also notice in the back of the room I set up a little swivel and I record the lectures. This is an experiment I'm doing. I'm trying it to see how it works. My intent, whether or not it actually works out this way or not is yet to be seen, but my intent is to record every lecture and post it in the online classroom. So if you happen to miss a lecture, you don't have to fall behind. You should still be able to get online and see the lecture. Now, does anyone, before we start on chapter 4.1, does anyone have any questions about chapter A1 from last week? A1 is in the back of the book, by the way. It's the A stands for appendix. I'm sorry, I said A1, it's A2. It's on page A1, A14. Any questions about last week? Everybody's good? Okay, well, if there are any, then if any come up, we'll be able to address them on Thursday during the review. So then in that case, everybody, haven't had enough coffee yet. Everybody turn to page 259. And we're going to start working on the right triangles, the trigonometric application. Everybody be sure and sign the attendance sheet. Is it going all the way around? Has anyone not signed in? You haven't? They make sure that goes around. Everybody make sure you sign in. All right, well, we all remember from the Pythagorean theorem, we know that c squared is equal to a squared plus b squared. Now we're going to look at the trigonometric functions, which are sine of theta, cosine of theta, tangent of theta. Well, what order do they put? Cosecant, secant, and cotangent. Cosecant, no, that's cosine. Secant and cotangent. And you will all discover, if you continue on in anything that involves the use of this, what you're going to discover is that you will almost never use any of the other three, cosecant, secant, or cotangent. These are the big three that you will use all the time when you work trigonometry. You have your calculator. It has sine, cosine, and tangent functions built into it, so you can just type in your angle, press sine, and it'll give you the sine of that angle. This is where those sines, this is where they come from. And you'll find that there's a reason that there's a reason that you need a calculator to get them for just an arbitrary angle, because they are, well, before they had calculators and computer algorithms to generate these numbers, they basically had to do, you had to have large lookup tables where you would find the angle that you want as close to it as you could get, look up the number. Let's look at the definitions. The sine of the angle theta is defined as the opposite divided by the hypotenuse. Well, the opposite of theta is b. Well, and I'm not going to try to finish spelling that. Which is, in this case, the side that is opposite the angle theta is b, and the hypotenuse is c. Similarly, the cosine of theta is defined as the adjacent side divided by the hypotenuse, which in this case would be a divided by c. These are the names that are assigned to the three sides of the right triangle. For the angle theta, the hypotenuse is always the hypotenuse. It's always the longest side. For whichever angle you're talking about, the adjacent is the side adjacent to the angle. The opposite is the side that has no part of the angle, that's opposite from the angle. Should be fairly intuitive. In the case here, we label the upper angle phi, then the adjacent becomes b, and the opposite becomes a. Now, the tangent of theta is defined as the opposite divided by the adjacent. Now I'm going to read these so I don't mess them up. We'll go ahead and look at the definitions of the cosecant, the secant, and the cotangent. Cosecant is hypotenuse over opposite. which in this case would be C over B. The secant is the hypotenuse divided by the adjacent. Which in this case is C over A. And the cotangent is the adjacent divided by the opposite. Which in this case is A over B. Now you remember I told you that you're almost never going to use these three? Does anyone yet see why that's generally the case? And whoever just came in, to make sure you sign the attendance sheet.
Our schedules got changed.
Okay.
Without us
Okay.
knowing.
Looking at these definitions, could anyone tell me why it might be that you don't ever really have to worry about these three, that if you have these three, that's all you're ever going to need?
They are the exact opposite of the top three on what's on top and bottom.
Yeah, you're right. The word is reciprocal. These are the reciprocals. And I hope I spelled that right, and if I didn't, you probably can't tell anyway, so it doesn't matter. Those last letters aren't really letters, are they? The reciprocal of the reciprocal of x is 1 over x. So anytime you invert a ratio, that's the reciprocal. The cosecant is simply the reciprocal of sine. The secant is the reciprocal of cosine, and cotangent is the reciprocal of the tangent. So if you once you've calculated one of the first three, you've got the second one, you just need to take the reciprocal of it. All right, those are the definitions of these trigonometric functions. And everyone remembers from algebra, you remember the definition of a function, right? These are functions they're functions in theta, in the angle theta. Now, we have our calculators now with all the trigonometric function buttons built in, so you type in the angle and you press the trig function and it gives you the value. But just so you know where these values come from, let's go ahead and work through a couple of these examples in the book on how to find a trigonometric function from a right triangle. And if we know the sides, if we know the lengths of the sides, then we can calculate any of the trigonometric functions as the ratio of the sides. So here they give us an example. Can everybody see this far over? They give us the example of the triangle that has a hypotenuse of 5. And then the opposite. First thing they ask is to calculate the value of the opposite. Well, I don't know how many of you have ever heard of the golden triangle or the golden ratio. This is it. But let's still work through the problem one step at a time. We know from Pythagorean's theorem that 5 squared will be equal to 3 squared plus, I'm going to call it b squared. So that gives us 25 is equal to 9 plus b squared. Subtract 9 from both sides and we end up with 16 is equal to b squared. Take the square root of both sides, and we have 4 is equal to b. So we know 4. This is why it's called the golden ratio. It's the only set of sequential integers that I know of that satisfies the Pythagorean theorem, so that 3 squared equals 4 squared, 3 squared plus 4 squared equals 5 squared. Now, once we know these, we can calculate the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. The sine is, somebody? Sine, opposite divided by hypotenuse. So that's going to be 4/5. Cosine, adjacent, divided by the hypotenuse, 3/5. The tangent will be the opposite divided by the adjacent. What's the cosecant? It's the reciprocal of sine. Yeah. So it'll be exactly 5/4. This will be 5/3. The secant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent, 4/5. Now, I told you that these are functions. So let's use that fact and work out this problem here, this example they give us in the book. We're going to look at building they call it constructing a rain gutter. Okay? We're going to start with a sheet of aluminum that's 12 inches long. Can everybody see this? Well, the entire length is 12 inches. Divided into 3 equal sections of 4 inches each. We're going to construct the rain gutter by bending this sheet of aluminum at the bend points. Yeah, make sure I'm using the same angles as they are. Equal angles on both sides. Bending them up to some height b. We know that's 4 inches. We know the hypotenuse here is 4 inches. Same on this side. We know that this length, A, is 4 inches. So now let's construct an equation that describes the volume of this gutter, the volume contained inside the gutter, as a function of the angle theta. Well, we know that the area of the gutter, the cross-sectional area, is going to be the value of the area of the two triangles plus the area of this internal rectangle. So, we have area of the rectangle plus area of the triangles. And we'll have 2 of those. So we have the total cross-sectional area is equal to 2 times the area of the triangles plus the area of the rectangle. And the area of the rectangle is simply 4 inches times the height b. And we know that the area of the triangle is, anybody remember from last week, from the first lecture? Half the height times the base. So it's going to be half this area of the triangle is equal to 1/2 the base times the height. And I'm using b for height, so I'm going to we know the base is 4 inches. So it's 1/2 b times 4. Or, dividing out the 2, each triangle is going to be 2 times b in area. And we have 2 of them. So we go back to our total area is now going to be 4b plus the area of the rectangle, which is 4b. And I don't think I'm following this exactly the way they do it in the book. Let's just go ahead and work it through and see if we get the same answer. What is b? That's what we need to know. How do we write b as a function of theta? Going to be the hypotenuse. We know that the sine of theta is equal to b divided by 4. Is that right? Opposite divided by the hypotenuse. So we can then multiply through by 4, and we have 4 times sine theta is equal to b. So we can come over here and add that in. We've got 4. You know what? I'm pretty sure I missed something because this is not looking at all like theirs came out to be. And I'm going to follow it through just to see where I end up. We can simplify this right now. It's 8b. And we know that b is 4 times sine theta. So that's 32 sine theta, which is not at all what they came up with. So where did I go wrong? Now they did a let's find out something here. Where did I go wrong on this? Because that cannot be. What would the maximum be for that equation? Real quick, I just want to ask a question. Who in here has had calculus? Anybody? Has everybody had algebra? Okay. Well, sine theta would be maximum when at 1. And I know we haven't gotten to that for y'all, so I'm just trying to figure out where I went wrong from what they did in the book. Because if I went wrong, you can bet it was me that went wrong, not the book. That means the maximum volume would be when sine is 1, that would be at 90 degrees. No, this is not right. I can tell you that this is not correct. So let's back up and figure out where I went wrong. Okay. They say we start with the area of a triangle is 1/2 times the base times the height, which in this case is 1/2. Oh. Anybody see it? This is not 4 inches. This is 4 inches. The hypotenuse is 4 inches. But this, the base, is not 4 inches. This was my error right here. Does everyone see that? As you bend this flap up, this side gets shorter. So, sorry, it's embarrassing, but everybody makes mistakes. Just learn from it. So, now we go back to our 3 areas. We have 2 times the area of the triangles, which is 1/2 B times A, not B times 4. Multiplied by 2. Then we have the area of the rectangle, which is B times 4 inches. And the total area is now B times 4 plus 2 times 1/2 plus B times A. So now we can factor out, that's our total area. Now we can factor out the B's, and we end up with B times 4 plus A is equal to the total area. Now we can talk about changing A and B into functions of theta. And we see that the cosine of theta is equal to the adjacent, boy, I really need to use different letters. The adjacent, which is A, times the cosine of theta is the adjacent divided by the hypotenuse. So it's going to be A divided by 4, or 4 cosine theta, multiply both sides by 4, and we end up with 4 cosine theta is equal to A. Again, 4 times sine theta is B. Now we can replace, am I getting too far away for y'all to see on that side? Now we can replace A and, I just realized nobody answered. Can y'all still see with me writing way over here? Okay. Now we can replace A and B in this equation so that B is 4 sine theta multiplied by 4 plus A, which is 4 cosine theta. And now we can start simplifying. We factor out the 4 here, and we get 4 sine theta times 4 times 1 plus cosine theta, which, multiply the 4's together, we end up with 16 sine theta times 1 plus cosine theta. And that looks a lot more like what they got in the book. Yep. Now, that 16 sine theta times 1 plus cosine theta. I'll put this over here for y'all to see it too. Now that is a function in theta that defines the volume of the cross-sectional area of this rain gutter that we're forming. In the book here, they show us this, that they include this graph of the function, and we could graph it out ourselves, and it would look something like this. It's gonna, well, yeah, I guess it would start off at zero, because it's just a flat sheet at that point. It has zero, nothing. You'll see if you graph it out, it does something like that, where you get this maximum at 60 degrees. And that would tell you that you could then bend it. You would know that if you want to create the maximum volume of water flowing through that rain gutter, you bend them to 60 degrees each. And let's we're going to need this. If we need it, we'll rewrite it. Let's talk about complementary angles. We're going to introduce the complementary angle theorem. Look at the word complementary. And this time I do need to be careful to spell it right, because it has to do with the point I want to make. Look at that part of the word. Complete. A complementary angle is an angle that completes another angle. If two angles complete each other, then they are complementary. Now the question then becomes, what's the finish line? What does complete mean? And it means two angles are complementary if their sum is equal to 90 degrees. In this case, this is a right triangle, and we know that the sum of the angles in any triangle must equal 180 degrees. Since this angle constitutes 90, we know that theta plus phi must also equal 90 degrees. Therefore, the two acute angles in any right triangle are always complementary. Everybody see that? Make sure we know that the right angle is 90 degrees. And we know that all three angles together must equal 180 degrees. Subtract 90 degrees from both sides. And theta plus phi must always equal 90 degrees in a right triangle. Therefore, they are always going to be complementary. Oh boy, they really get this confusing. I'm going to try to do this the way they do it in the book, but I'm going to have to watch what I'm writing. Watch while I copy it because... Okay. We have the right triangle. They label the sides A, B, and C, where C is the hypotenuse. It's, and as always, it's opposite of the right triangle, of the right angle. And so they label this angle uppercase B because it's opposite side B. And they label this angle uppercase A because it's opposite side A. And then they intentionally, I swear it has to be intentional, they intentionally try to confuse you by pointing out that adjacent to that uppercase B is adjacent to lowercase a, and uppercase A is adjacent to lowercase b, and just look at the picture. Okay? Don't try to recite that. It's, for the record, the standard isn't, if it isn't, it should be. For angles, use Greek letters. This gets too confusing. But now, they're going to show it. What they're going to say is that the sine of B, of this angle, the sine of B, is this B, the lowercase b divided by lowercase a. That's our definition, right? But that would be the cosine of this angle, A. The cosine of this angle would be the adjacent divided by the opposite, which is B divided by A. Go ahead.
Isn't the sine of the B over C?
You know what? I think you're right. I'm using the wrong one, aren't I? It's C, not A. Did I write that? Yeah. It sure is. Thank you. B over A would be what? B over A would be what? The tangent of the uppercase B. But here we see that the sine of angle B is equal to the cosine of angle A. Similarly, and I don't know why they, well, yeah, they do it. So we're going to do it. The cosine of B is equal to A over C which is equal to the sine of A. Then finally, going back to where I started, albeit not on purpose, the tangent of B is equal to B over A, which is equal to what? The cotangent of A. Now, let's look at the reciprocals of these. what would be the cosecant of B? C over B. But that is also the secant of A. And then you can see the other, obviously the cotangent of, no, I'm not going to jump ahead. I'm going to take this one step at a time. Look at the secant of B, which is C divided by A, because it's actually the reciprocal of the cosine of B. And that is equal to the cosecant of A, and then finally the tangent, the cotangent of B is equal to A over B, which is the tangent of A. What this shows is what's called the complementary angle theorem. And to simply write it out in English, complementary angle theorem cofunctions of complementary angles are equal. In other words, if you have one angle is 30 degrees, then the other angle has to be 60 degrees. The cosine of 30 degrees then is equal to the sine of 60 degrees. Now here, in example 3, they're just showing you how to, basically they're showing you how to subtract an angle from 90 degrees to get the complementary angle. But they do introduce something that's kind of interesting here that we haven't covered yet. So I'm going to take a moment and discuss this for you. Many of you have looked at your calculators and noticed you have buttons called degrees, radians, and probably have one called gradians. Okay? I have never once in my entire life used gradians. I think it divides a right angle. I don't know. I really don't know what gradients are. I'd have to look it up. It's never been an issue. But you do need to know the difference between degrees and radians, because you always need to make sure you're working in the right units. So technically, degrees and the radians, neither one are units. In fact, they are unitless numbers. Everybody knows degrees. The full circle is 360 degrees. A straight line is 180 degrees. A right triangle is 90 degrees. Radians come from dividing the circumference by the diameter. And everyone knows the ratio of the circumference to the diameter is pi. If you're looking at a full circle in radians, that is 0. And by the way, in case, I don't know if y'all have seen this yet or not, this is again standard notation. In fact, you may have seen that this is called the unit circle approach to trigonometry. We're going to get to the unit circle. We haven't gotten to it yet, but when we do, this circle is divided into quadrants 1, 2, 3, and 4. This is 0 radians. This is pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. So 0 and 2 pi give you the same. Radians are unitless numbers. If you are working a problem that gives you angles in terms of radians, you need to put your calculator in radian mode. So learn how to do that. Everybody, I'm sure some of you have different calculators than the others, so everyone find out on your own calculator how to switch between radians and degrees. So, I point this out because in this example that we got to here, they say the sine of 62 degrees is equal to the cosine of what? Well, 90 minus 62 is 28. So the sine of 62 degrees, without knowing exactly what value that is, we do know it's equal to the cosine of the complementary angle 28 degrees. In B, you'll notice they switched from degrees to radians. Look at number C, or letter C. That introduces something that you haven't seen yet. It's one of the fundamental trigonometric identities. So let's look at problem C here on this example number 3. We start off with sine squared of 40 degrees plus sine squared of 50 degrees. Now, again, I want to stop here and because I know we haven't discussed this notation, so I want to make sure you understand this. Everyone knows what a square is, but in terms of trigonometric identities, when you have sine of 40 degrees is some value. Some value x, whatever that value is. X squared would be written as sine squared 40 degrees. This is the same thing as that. Okay? So when you see trigonometric functions written this way, sine squared something, cosine squared something, that's what it is. That's how you write the square of the function. So, now here, they point out what's the complementary angle of 50 degrees? 40 degrees. So this then could be written as sine squared of 40 degrees plus cosine squared of 40 degrees. And they just tell you that it's equal to 1. This is a trigonometric identity, and we're going to get to the trigonometric identities later in the semester, but since they brought it up in this chapter, I want to, and if we were going through the book in the order of the chapters, we would have covered this a couple weeks ago. Sine squared theta plus cosine squared theta is always equal to 1. Remember, it's called the unit circle approach. The unit circle is a circle whose radius is equal to 1 unit. So, the sine of theta is equal to, look at our definitions. What is sine of theta? B over C. Since that is C and that is B, we know at x equals C and y equals B, the sine of theta is B over C, and I'm sorry, I'm messing you up again. The C is the hypotenuse, not the adjacent. Sine theta is B over C, but C, because it's a unit circle, is equal to 1. So sine theta of the unit circle is just the y-coordinate B. Similarly, cosine theta is A over C, but C is equal to 1, so the cosine theta on the unit circle is just C. I'm sorry, A. The x-coordinate A. You'll also notice that the x and y coordinates inside this circle are always going to be 1 or less. If we ignore the fact that in this case C is equal to 1, we could solve for sine theta and we would find that C times the sine of theta is equal to B for any radius C. Similarly for the cosine. But again, in this case, because it's a unit circle, the hypotenuse is equal to 1. Sine theta still equals B. What do we now knowing this about sine and cosine, let's add in the Pythagorean theorem. And we now can say that A squared plus B squared is equal to C squared. Well, A squared is cosine theta, cosine squared theta. B squared is sine squared theta. And that's equal to C squared. But on the unit circle, C is equal to 1. And so we have the trigonometric identity that sine squared plus cosine squared equals 1. That's how they got the solution on this problem, on this example for letter C. Now, they're introducing, going back to the book now, they're introduced the, I guess they call it the right triangle theorem. All right. Before I continue on, I have a does anybody have any questions about anything we've covered so far? Have I thoroughly confused everybody yet? Yeah. Don't count me out on being able to do that. Sorry? Yeah. Well, everything, it's called the unit circle approach for a reason. Everything follows from the fact that in a unit circle, you have a radius of 1. So 1 times the cosine of the angle equals the x value. 1 times the sine of the angle equals the y value. But these definitions, they're told, I have been told that the better way to start this course is with the definitions that we just introduced for any angle based on the right triangle. The opposite divided by the hypotenuse is the sine of the angle. The adjacent divided by the hypotenuse is the cosine of the angle. Once you get these relationships sorted in your head, the opposite side divided by the adjacent side is the tangent of the angle. Those are the 3 that you need to remember. The rest you can sort out. And then when we get to the unit circle, and C is now suddenly 1, you can square it, you can ignore it. It just, when it shows up in the denominator, it's just divided by 1. When it shows up in the numerator, it's just multiplied by 1. It becomes an identity. They say the best way to sort things out is to work through them, to use them. So let's work another problem. And we'll just keep working problems until, I guess, we run out of time. Is there anything else I need to introduce? No, I think that's the complementary. I do want to make sure y'all get this. For a right triangle, C, A, and B, and theta, and phi, it is always true by the Pythagorean theorem that c squared is equal to a squared plus b squared. And by the complementary angle theorem, it is always true that theta plus phi equals 90 degrees. Or in radians, pi over 2. So let's see if we can use some of this and work some of these examples. They give us figure 8. They say if b is equal to 2, I'm sorry?
Does 90 always equal pi over
90 degrees is always pi over 2. And let's look at that. That's a good question. Let's look at that. Here's your circle. Here's 0 degrees. Here's 180 degrees. 270 degrees. 90 degrees. Going all the way around this circle is 2 pi radians. No, 270 is here. Degrees. No, yeah, that's a 7. What is pi? Pi is the ratio of the circumference divided by the diameter. So the circumference all the way around is pi times the diameter. But the diameter is just 2 times the radius. So 2 times the radius is equal to the circumference. So once you've come all the way around, you've come 2 pi radians. Understand this. When you measure, this will probably make more sense to you. When you are working in radians, if you multiply a radius times an angle in radians, it will always give you the length of this arc, of the arc subtended by the angle. That's why people use radians. So if you take the unit circle and you sweep out the full circumference, full 360 degrees, the length of your arc is 2 pi radians, or 2 pi times the radius. You see, radians, radius, 2 pi times the radius is the length of the arc that is swept out. That's why they introduced radians instead of just doing everything in degrees in the first place. So, go back to working a problem so we can at least see how to do this sort of thing. Let's say we get a triangle. A, C, and the height is 2. Then they give us this angle that they call uppercase B, and this angle they tell us is 40 degrees. Then they say, let's find A, C, and B. Well, right off the bat, we know that the sum of the 2 acute angles is always going to be equal to 90 degrees. This is 40 degrees. Plus B then must equal 90 degrees. Subtract 40 from both sides, and we get B equal to 50 degrees. Now they want us to find the 2 sides, the 2 unknown sides, A and C. Well, if we knew this length, then we could multiply that length times we would know that C times the cosine of 40 degrees is equal to 2. So we could figure out, does everyone see that? What's the cosine of 40 degrees? The cosine of the angle is the adjacent divided by the hypotenuse. And I know that they take a different approach in the book. We'll come and look at how they do it in the book. But I want to show you that there's always more than one way to skin a rabbit. We know that the cosine of 40 degrees is equal to 2 divided by C. 2 is the adjacent side. So we can multiply both sides by C and we get C. Boy, I got to. See if this one works any better. C times the cosine of 40 degrees is equal to 2. And you got your calculator. You can get the cosine of 40 degrees. Divide both sides. We get C is equal to 2 divided by cosine 40. Two is the adjacent of 40 degrees. It's the opposite of angle B. If we were looking to write an equation for B, we would write, what do we know? We know the opposite is 2. We can divide by A, and that would give us the tangent of B. I think in the book they use the tangent of 40 degrees, which, what's the tangent of 40 degrees? The opposite divided by the adjacent. So in this case it would be A divided by 2. Or 2 times tangent of 40 degrees is equal to A. Oh, look at that. They did use cosine 40 for finding C. And they give us approximate values where they actually punched it into the calculator and got the answer to a couple of decimal places. Just real quick, I'm going to ask, does everyone here know how to use your calculator to calculate sines and cosines? Let me rephrase. Does anyone not know how to use their calculator to get these values? And depending on your calculator, it could be different. Yeah, if you have a standard cheap Radio Shack calculator like I use, then you would type in, you make sure it's in degree mode, you punch 40 for the number of degrees, and then press whichever function button you want, sine, cosine, tangent. If you already have the value of sine, you know the value of the sine, but you don't know the angle, then you would take the inverse of the function. But we'll get to that, I guess. It's already confusing enough, right? I don't want to get too far ahead. Take this in little tiny steps. Figure 9, example 5. Let's go ahead and work some of these examples while we have time to do it. And remember, Thursday, the whole period is review of both last week's assignment and this week's. Get ready for the exam next Tuesday. So, if y'all have, You're working these assignments, when you start working this week's assignment, make a point of making notes of any questions you have. We can work through some of these problems. As he observed, working through the theory behind all of it, and looking at the definitions and how to algebraically manipulate them is all well and good. But to really learn the material, to really sort it in your mind and to get a grip on it, to get a good understanding of it, you need to work through problems. So let's work through another problem. Here we're going to use, on page 262, if you're following along, it says use a figure 9 as a right triangle with sides 2, 3, C. This angle they're calling B. This angle they're calling A. Now, they want us to find C, B, and A. Okay, well, who can tell me just off the top of your head, how do we write the equation to find C? Pythagorean theorem. Exactly. C squared equals 3 squared plus 2 squared equals 9 plus 4 equals 13. So C equals the square root of 13. That's a weird one. And according to the book, the square root of 13 is approximately 3.61. I just told y'all. I just mentioned this, and now look, we're going to use it. So I guess I'm going to introduce that notation to you too. Let's start by finding A. What do we know about A? Well, we can write that the tangent of A is equal to the opposite divided by the adjacent, which is, in this case, 3/2. That means that if we want to find A, we know the tangent of A, then we can write A is equal to the inverse tangent of 3/2. Does everyone recognize the inverse notation? From algebra, superscripts, exponents. Negative exponent is 1 divided by, a negative exponent is simply a reciprocal. X to the minus 1 is equal to 1 divided by x, the reciprocal. X squared, x to the minus 2 is equal to 1 over x squared, etc. Well, here, if you know the tangent of an angle and you want to find the angle, you punch in the tangent punch in the value of the tangent into your calculator, and then you hit inverse tangent, and it'll give you the angle A. As an exercise, let's everybody try this now with your calculator. Punch in 3/2 or 1.5, and then put in inverse tangent. Yeah, I'm not even going to figure out how to work this one. Not on the fly. What answers did y'all get? Everybody got something? It's 56.3 plus some more digits? Okay, then you did it right. Okay. Degrees. Now, how do we find B? We know that 90 degrees is equal to B plus 56.3. Therefore, subtract 56.3 from both sides. And I'm not even about to try and do the arithmetic in my head. Comes out to 33.7. Hey. We got time to do one more, so let's do this applied problem they use here. Surveyor has a river. And I bet you I drew that river going the wrong way. I sure did. Want it to go up so I can make the... This is a river. Surveyor wants to measure the width of the river from here to here. So he marks this point. He travels over here with his transit. How far did it say he goes? 200 meters. He then uses his transit to measure that angle theta, which he finds to be 20 degrees. How do we find out the width of that river? Well, here's our right angle. There's our opposite side. And we can immediately write that the tangent of 20 degrees is equal to A divided by 200 meters. We multiply both sides of the equation by 200. We get 200 meters times tangent of 20 degrees is equal to A. We'll put in 20, find the tangent, multiply that by 200. What do you come up with? 72.79 or 72.8. So basically about 73 meters. Anybody have any questions? Yes? No? Did everyone sign the attendance sheet? And where is it? Who has it? Up there. Is everybody signed in? Okay. Before you get up and before everybody gets up and disappears, anyone that has their homework ready, turn it in from last week. The rest of you have, the extra week to get it done. But in class.
What was the assignment for people that weren't here?
Nobody was here. The class was canceled. But it's in the syllabus. And it's online. It's posted online. Thursday we will do the whole hour, the whole period will be review of last week and this week. Working any problems. Preparing for a test. Your first exam. A week from today. For the exams, you may have a 3x5, a standard index card, 3x5 card, front and back. Write any of the identities, the definitions, whatever you need written on it. See you Thursday. Just hand it to me. Thank you.
So when we do it, do we like print it off and turn it into you?
It can be handwritten as long as I can read it. Make it neat.
Thank you. We cannot use these calculators.
No, that's right. That's a case calculator.
I need to figure out how to use the other ones. Yeah.
I think. Yeah, this one would be okay, but it's a strange calculator to me, and I'm not sure whether it uses RPN or no, just works normally. Okay, but
I have one at home.
Okay.
Mess with it. Okay.
Thank you. See you Thursday. Good morning. Say again? Boy, ain't it? Over the break, I had to work at home, but I didn't have a choice because I got here and they'd turned off the heat and they'd locked off the thermostats. Couldn't stay in these rooms. We're ready for our first lab. Yeah, well, that makes some of us. This is an electrostatics lab, and I dread it. I dread doing electrostatics. When you've gone through and you've studied electronics and electrical, E&M, and you have the, you measure currents and you do all that. Going back and dealing with these static electricity, getting things to charge, and it's like, okay, wait, which one's the acetate, and which strip is the acetate, which strip is the vinyl, which piece of cloth is woolen, and which piece of cloth is rayon. It's like, and if you use the wrong material and with the wrong cloth, it doesn't want to charge right. And we'll struggle through it. Don't worry about it.